Well, good afternoon and welcome to this live stream of the California Academy of Sciences Tour of the Universe. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences, and I'm going to be your tour guide today. The imagery that you're seeing is coming from free open source software called OpenSpace, and it's actually running on a server room at the California Academy of Sciences, whereas I am delivering the audio here from the comfort of own home. So if you hear sirens in the background or my cat interrupt us, you know what happened. But in the next half hour, what I'd like to do is take you from the International Space Station, where we're starting our show, out to the cosmic microwave background. That's a huge distance to travel. So I'm going to get started right away. While you were waiting for the show to start, looking at the International Space Station. This is a great place to start our program because it's a nice human scale. The total length from one end to the other, from sort of this side to this side, is about a football field. Whether you think of football fields in the European sense or the American sense, about the same. And you can imagine that each one of these little canisters is home to astronauts, including those two poor astronauts sort of stuck on the ISS for a while. And you can get a sense of how far we go out into space these days. This is it, a few hundred kilometers above Earth's surface. And you can see some city lights down there in the distance. Basically, the ISS in our model here is on the nighttime side of Earth. I'm going to go ahead and add the orbit line here, which is that line that's sort of connecting from the lower right of the screen. That's showing us the trajectory of the ISS in its orbit around Earth. You'll notice the limb of our home planet Earth are showing up on the right-hand side of the screen. That's the lit side of Earth, the daytime side of Earth. And as ISS continues its orbit around Earth, it's traveling from daytime into nighttime, as you kind of saw in the lead up to this live stream. Now, you can see how high ISS gets in our perspective here. That's a few hundred kilometers, a few hundred miles above Earth's surface. And that's space. Certainly, people are paying to go even lower than that out into space to claim that they've been into space. But it's not too far out into space. And in fact, during today's show, we are going to travel much, much, much farther from home. So right now we're seeing Earth as a whole. You can see, if you know your geography pretty well, Europe is over there on the right-hand side. The North Pole is kind of the left-hand side. North Pole is kind of facing to the left. Africa is very prominent in the top part of our view. And that sort of bright image behind Earth is how we represent the sun, with that little orange disk in the center. And then the stars in the background. If you're really good with constellations, you might recognize Scorpius here, the scorpion in the sky. And this hazy band that crosses almost directly through the center of the image is our Milky Way. Now, we're going to travel much farther than any of the objects we're seeing in the image right now. Earth is our starting point, our home in the universe, but we've got a lot of interesting stories. I often do a program called Universe Update, which is when I do a little bit of this tour of the universe plus a lot of news about what's happening in astronomy, and I couldn't resist. I'm going to at least talk about one news story before we end our show today. But again, this is our starting point, our home planet, third rock from the sun, Earth, the place where everyone you've ever known has had their home. All the history you've learned about civilizations and people has taken place on this tiny blue dot that we're traveling farther and farther away from as we go. Now, I don't know how good the Facebook or YouTube streaming is, but if you can see this little dot here, that's actually Earth's moon. And so what I'd like to do now is bring up some additional markers. In this case, we previously saw the orbit of the ISS, the International Space Station, around Earth. Now we're going to see the orbit of Earth's moon around our home planet. So the moon is currently sort of in between us and the sun, kind of getting toward a new moon. And the moon, if you want to think about that, is as far as humans have ever traveled out into space, much farther than the the International Space Station. It's about 250,000 miles from Earth to the moon, or about 400,000 kilometers. And basically a bunch of astronauts back in the 60s and 70s were able to make that trip from Earth to the moon, and that's as far as humans have ever traveled. Sorry, we have a question that I kind of breezed by, but the question was, are the Starlink satellites, which are satellites being launched right now, higher or lower than the ISS? It's a great question. The Starlink satellites are a little bit higher, maybe about 400 kilometers above Earth's surface. The ISS is a little more like 200 kilometers or less above Earth's surface. So just a great question there about the altitude of the ISS versus Starlink satellite. And yeah, those are, of course, people on the Starlink satellites. Those are satellites that are used for communications, and they are orbiting at a much higher altitude. So, oh, sorry, somehow I managed to allow some windows onto the screen there. I didn't mean to do that, but actually that's a good prelude, because you're going to be seeing a little bit of the interface for the software a little bit later. So just to recognize that what you're seeing here is really just one monitor on a virtual computer that we're broadcasting out onto YouTube and Facebook. So keeping in mind that distance from Earth to the moon, 250,000 miles, 400,000 kilometers. If you want to think about that in terms of light travel time, that's going to be a standard distance that we use a lot in this program, because the distances get really large and harder to articulate and wrap your head around if you always use miles or kilometers. So just to use as a benchmark, our distance from Earth to the moon is about 1.5 seconds in terms of light travel time. So you can think of that as like a pause in conversation. When you look at the moon in the sky, you're seeing as it was about 1.5 seconds ago. Now the sun, once again entering our frame at the bottom, is about 8.5 light minutes away, which means it takes light 8.5 minutes to reach Earth from the sun, or vice versa. And the lines that you see crisscrossing in front of the sun are actually the orbits of the other planets in our solar system. So let's go ahead and keep pulling back here. And I mentioned 1.5 seconds in terms of light travel time from Earth to the moon. That's a pause in conversation. 8.5 minutes, maybe that's from the sun to Earth. That's a quick lunch. You can see the inner planets now: Mercury, Venus, Earth, and Mars, the 4 what we call terrestrial or Earth-like planets in orbit around the sun, meaning they're all relatively small, rocky worlds. Earth is the largest of those 4. But the 4 outer planets, or giant planets, are quite different. We see Jupiter and Saturn here, and then farther in the distance, we have Uranus and Neptune. Before we leave the solar system, because we do have a lot of distance to travel, I want to take us to visit a location in the solar system, a moon of the planet Saturn, which you may have heard of, called Titan. Now, to do that, as I mentioned, I'm going to actually reveal some of the interface of the software here, not the Windows interface that we saw a moment ago, but instead the software that we use called OpenSpace. Again, this is actually NASA-funded open source free software that you can download yourself. You'll notice that it has a menu here, and what I'm pulling up is asking it to target our moon here, the moon Titan. And then I'll go ahead and get rid of that just for now and just fly us to Saturn and to its giant moon, Titan. Now, we don't currently have any spacecraft in orbit around Saturn. And here you're seeing, just, you know, Saturn down here in the middle and the orbits of some of its moons around the planet. And I'm taking you to, again, Titan, the largest of those moons. And we'll definitely take a look at Saturn before we get too far away too, because it is, of course, a beautiful gem of the solar system. And as we zoom in here, we're actually going to show you some details that you can't see without using special instruments. But what I'd like you to notice is that Titan is, in fact, kind of this hazy, cloud-covered moon. And it actually has an atmosphere almost as thick as Earth. And in fact, that's one of the only other places in the solar system where something with a solid surface has an atmosphere like Earth. Let me go ahead and just take away our those crisscrossing orbits of the planets just because they're kind of confusing here in the background. But here we can see this hazy atmosphere. And in fact, when the first spacecraft that visited the Saturn system took a look at Titan, all they saw was this sort of tennis ball, this sort of featureless atmosphere, thick atmosphere covered hazy moon of the planet Saturn. What you can see kind of peeking here underneath is a little bit of a cheat. What we've done is allowed ourselves to see through the atmosphere a little bit. If we were in orbit around Titan like this, we wouldn't actually see this detail. Instead, we observe mostly in infrared. But you can actually, by observing Titan using the cameras on the Cassini spacecraft, and which orbited Saturn for many years, and by sending a probe, the Huygens probe, down to the surface of Titan, we've learned that Titan is actually covered with a sort of collection of lakes and maybe oceans of liquid methane and a surface of frozen ice. And this atmosphere is actually made of methane and ethane. Now, recently, in the past couple of weeks, the research team at the University of Hawaii announced that they had used a computer model to study how the surface of Titan may sort of store methane. And the motivation was to look at why there were so few like deep craters on the surface of Titan. The surface seems surprisingly smooth, and so they were using a computer model to see how the different chemical constituents of the crust of the moon could react differently to impacts and allow the surface to sort of smooth out faster than a purely like thick icy surface. Thick icy, by water ice I mean water ice. And so what they found is a methane-rich crust, maybe 6 miles or 10 kilometers thick, could produce this sort of result. And that might also be where a source of the methane that creates the thick atmosphere of Titan comes from. So just an interesting result, and I wanted to talk about it briefly before we left the solar system altogether. Not a new observation of Titan, but rather work that builds on the decades of observations made by telescopes and spacecraft of this icy moon of Saturn. And since I've mentioned Saturn, let me go ahead and just give us a quick look at Saturn, and to be able to enjoy a view of the moons. So I'm going to go target Saturn. Of course, it's right there, but that means that our camera is pointed directly at our lovely ringed planet. And this is a great view of this dramatic planet in our solar system, this amazing feature of the moon, of the rings of the planet, which seem to have some kind of banding on them in my view of the software. I'm not sure where that's coming from. That's not something we see in our photography or our visuals of the planet. It doesn't have that striped look to it. At least the stripes that are going sort of into and out of the screen. So these structures, that seems to be an artifact of the software, but the rings of the planet and the gaps in the rings and the brighter areas and darker regions of the rings are features that we have observed for many years. It was kind of a great puzzle initially, but we now know that is actually, the rings are actually formed from billions of tiny little moonlets, little tiny objects in orbit around Saturn that kind of blur together from our perspective to create the rings of the planet. So with that, let me go ahead and pull away from Saturn for a moment. And we'll go ahead and kind of hit the gas pedal a little bit and pull away from our solar system as well. Let me go ahead and bring back our planet trails, our planet orbits, so that we can see this a little more clearly, and continue moving away from our solar system. So now we see our sun here at the center and the planets in orbit around it. I just want to note that if you look at the outermost planets, so we have, again, Mercury, Venus, Earth, and Mars down here close to the sun, Jupiter, Saturn, Uranus up here, Neptune over here, farther from the sun. if you think about those distances in terms of light travel time again, the distance across Neptune's orbit, a little hard to see here, but all the way across Neptune's orbit is about 8 light hours. So it takes light about 8 hours to cross from one side of Neptune's orbit to the other. But the closest star to the sun, and it looks a lot brighter and fuzzier than our sun because we're making the sun sort of artificially dim here. But this star, Alpha Centauri, is the closest star to us other than the sun. It's about 4 light years away. So if you want to think about that for a moment, the distance from Earth to the moon is 1.5 seconds of light travel time, distance from Earth to the sun, 8.5 minutes, the distance across our solar system, 8 light hours, but the nearest star is 4 light years away. So if we compare that distance across our solar system, 8 light hours is like a good night's sleep. But 4 years is more like a high school or college education. So the difference between sort of planetary kind of distances in our solar system, versus interstellar distances to nearest stars, is like the difference between a good night's sleep and a high school or college education. And what's important to note too, and let me just add one other thing to help give some sense to this, is that although we've sent spacecraft out to explore our solar system, we've never sent spacecraft to other stars. So I want to put up the trajectories of some of our fastest traveling spacecraft here. These 5 trajectories show 5 of the 5 spacecraft that we've launched fast enough to eventually escape the gravitational pull of the sun. Everything else we've sent out into space will essentially orbit another planet or orbit the sun. These 5 objects are traveling fast enough to escape the sun altogether. Now, 4 of these were launched back in the 70s, the Pioneers 10 and 11 and Voyagers 1 and 2 spacecraft. And then this one is the New Horizons spacecraft launched in the early aughts. But and we're projecting them out to their current distance from the sun based on our understanding of their trajectories, of their motion away from the sun. And if you look at this, the 2 most distant objects, which are actually the doesn't look like that from the way we're looking at it. Voyagers 2 here and Voyager 1 here. Those are the 2 most distant objects, most distant spacecraft. And they've only traveled, and you can compare, since this is about 8 light hours and a day is 24 hours long, none of these objects have traveled more than light travels in a single day. And yet these are the fastest sort of nuts and bolts objects that we've sent out into space. So what we've learned about the stars, we've learned by studying the light from the stars and teasing apart properties of light that help us understand what's happening in the universe around us. Well, I really hit the gas now. So we moved away from our sun, which is still there at the center of the image. And what we're going to do is take a quick look at local stars, but then pretty quickly move out of the Milky Way so we can get to the punchline that we promised on Facebook earlier today, which is to understand a little bit about the cosmic microwave background. So we've pulled away from the sun's location here, but we're continuing to sort of orbit its location in a 3-dimensional data set of stars. So everything I'm showing you here is based on astronomical observations of the universe around us. The image of Titan with its atmosphere is based on imagery we have from the spacecraft. You didn't see much of Earth when we started, but that's all based on mapping of Earth. And the locations of each of the stars in our data set is based on observations of the stellar's distances and brightness and properly located in 3 dimensions. So if you know your 2-dimensional night sky constellations, you might recognize Orion here, the square of stars with 3 stars in the center, representing a hunter with a tiny little head and a sword dangling from his belt. The V-shaped collection of stars here is called the Hyades, with a bright star on. This is a cluster of stars in the sky that in constellation terms is usually described as the head of Taurus the Bull. And then this amazing and probably hard to see tiny little cluster of stars, the Seven Sisters or the Pleiades. So we've traveled very far away from the sun, but we haven't traveled far enough that the constellations are completely unfamiliar. That's going to change as we go farther and farther from the sun, though. And eventually we sort of leave the local stars behind. You'll notice that Aldebaran is a little closer than the other stars in the Hyades. So the kind of reddish eye of the bull actually got sort of yanked out of its socket there. And then as we travel farther away, what we're going to do is do a little bit of a transition to look at not just stars, but at the collection of stars in which we live. So we've now traveled hundreds of light years from our home, still seeing a part of the catalog of stars in our galaxy. And you'll remember that I pointed out the Milky Way very early in the show. It was the hazy band of light that crossed almost in exactly the same position it is now, from the upper middle of the screen to the bottom of the screen. But here what we can see is a representation of what the Milky Way really truly is, which is the band of light encircling us is actually a great sort of pancake-shaped, frisbee-shaped collection of stars with hundreds of billions of stars that we call our Milky Way galaxy. Now, there are some hazy little dots here in the background. I'll get to those in a moment. The Milky Way is a collection of hundreds of billions of stars, as I mentioned, as well as dust and gas, stuff that makes up stars, the stuff that is left over after stars go supernova or otherwise evaporate into space. And since we've been talking about distances in terms of light travel time, the distance from one side of the Milky Way to the other is about 100,000 light years. Now, we start talking about a second and a half in terms of light travel time, and then 8.5 minutes, 8 light hours, 4 light years, so all very human timescales. But 100,000 light years, 100,000 years, that's how long our species has been around on the planet. Our species hadn't even left Africa 100,000 years ago, or was leaving Africa maybe 50,000 years ago. So this is a very different sort of scale in the universe. And we can see here two satellite galaxies, the large and small Magellanic Clouds. And they appear as hazy bands or hazy little blotches of light in the southern hemisphere. But these additional little circles in the background actually represent the location of other galaxies. So now those aren't other stars. Those are other galaxies, collections of, again, hundreds of billions potentially, or maybe even some of these, the larger ones, trillions of stars. And what's interesting to note here is that the galaxies aren't sort of uniformly distributed in space. They kind of clump and cluster together. So we haven't gotten quite far enough to see the Virgo cluster, but I think we might actually be passing right by it here. So over here on the right-hand side of the screen, you can see there's a nice, big, bright clump of dots. That's the Virgo cluster of galaxies. It's easily seen as a little bit different and clumpier than some of the other galaxies in our 3D model here. Again, each of these galaxies is an accurate location in three-dimensional space. We're color coding different galaxies by different surveys in which they appear. So the purplish kind of galaxies are a different survey from the other ones. But the main thing, again, wanting to note is that the galaxies are not sort of uniformly spread through space, but they clump and cluster together. And that's an interesting question. And we'll get to the sort of a bit of a punchline on that at the end of the show here. But I also want to point out something, and that's real, I should note, the galaxies really are clustered together. But there's something else that's an artifact of how we observe the universe around us. So you'll notice that there's kind of a gap at the top and the bottom, the sort of wedge-shaped gap at the top and the bottom of this image. And the galaxies look like they're spread out in sort of a bow tie shape. And that's not because there are no galaxies in the top middle and the lower bottom middle. That it's not that there are only galaxies where we're displaying them here. It's that these are the galaxies whose distances we've measured. We have measured a few in that sort of gap, but not many. We're showing the locations of hundreds of thousands of galaxies here, but most of them are in the surveys that have covered only a portion of the sky as seen from Earth. And because of that, we have this incompleteness, this regions where we're not seeing any galaxies, simply because we haven't measured the locations of galaxies that are there. As we pull a little farther away, I know that this is the point at which our compression for video transmission gets a little clunky. So I'm guessing that you're going to see a little lack of smoothness here as we pull away. So I'm going to try to slow things down a bit. But as I continue to pull away from our location in the center of this model of the universe, of the center of this three-dimensional data model, I want to point out that it's a little confusing because it looks like we're at the center of the universe, but that's not the case. It's just that we are the ones drawing this picture. So we're the ones who are plotting the distance of all of these objects away from Earth. And this is a self-consistent way of describing where things are in the universe, but it can be a little confusing. So we're flying away kind of right along that notch in the data, the absence of data, but we're still here in the middle of some bright circles representing actually not even galaxies anymore, but rather representing the bright cores of young galaxies that we call quasars. Now, we don't see quasars near home. Quasars are something we see early in the history of the universe, but not close to home. And what I mean by that is that because, as we've been talking about from the very beginning of the show, light travels at a finite speed. When we look at objects that are far away, we're seeing them as they existed in the past. So we don't see quasars close to home because they existed early in the history, or earlier in the history of the universe. And as the universe has grown older, we have fewer and fewer quasars. So we see them far from us, but not nearby. Because looking out into space is looking back in time. So when we look along a line of sight, farther and farther away from us, we're seeing farther and farther into the past. And the punchline to that, and by the way, this is the image that we posted on Facebook this morning or something similar to it, this mottled kind of black to red to white image in the background is what we call the cosmic microwave background. It is not an image like the surface of Titan that we saw. It's not an image like the view of Earth that we saw. Instead, this is sort of like almost literally a heat map. The dark regions in this background, and it's kind of obscured by the quasars here in the foreground. Those dark regions correspond to relatively cool parts of the universe. The bright kind of whitish regions, which are kind of behind the quasars here, correspond to hot parts of the early universe. So let me kind of turn so we can see this more clearly. And this is actually the oldest light in the universe. It dates back to when the universe was only about 380,000 years old. But the universe today is about 13.8 billion years old. So the universe was very, very young indeed when that light was released and eventually to be collected by our telescopes here on Earth or in orbit around Earth. There's a question about, could the burnout remains of early universe quasars account for dark matter? And the answer is probably not. The dark matter effect is something that we see earlier than the existence of quasars. And actually, the cosmic microwave background gives us a hint as to what happened, because those dark regions are not only cooler than the bright regions, they're also less more dense. The cool regions are more dense. The bright regions, the hotter regions, are less dense. So this ancient light from the early universe tells us that there was a difference in density in the early history of the universe. The cooler, darker locations in the map represent denser regions. The brighter, hotter regions represent less dense regions. And what we understand now is that that variation is tiny. Cool parts are only about 1 part in 100,000 times cooler than the hot parts. And the density is about the same. The cool parts are only about 1 part in 100,000 times denser than the hot parts of this image. And so that structure that was baked into the very early history of the universe was actually what eventually evolved into the clusters of galaxies that we see close to home. And that action was driven by dark matter. The way that you can take that tiny fluctuation, 1 part in 100,000, to form these dense collections of galaxies is if there is matter that we're not seeing that is having an effect on the evolution of galaxies and galaxy clusters. So dark matter played a role early in the history of the universe to take that tiny fluctuation of the cosmic microwave background and shape it into the clusters of galaxies and the galaxies that we see nearby, as well as at a smaller scale, planetary systems and planets themselves. So with that, this is our kind of big picture view at the end of our tour of the universe. I'm going to ask the computer to make sure that we're pointed directly at Earth to take us home. And I'm going to go ahead and slowly at first and more quickly as we move, fly you back into toward our own home, our own solar system, which again is somewhat confusingly at the center of this three-dimensional image, simply because we're the ones drawing the picture. So we're kind of moving in toward that butterfly-shaped or bow tie-shaped collection of galaxies. We'll go ahead and fade the cosmic microwave background out so that you can see the individual points in these surveys, giving us locations of these galaxies in the universe around us. The distant quasars form this kind of the big red wings stretched out to the right and left of our image, but the sort of brighter yellower and greener dots in close to the center are parts of the survey that show the locations of individual galaxies. As we move into the very center of our collection of data, what we'll see are 30,000 some odd galaxies that are relatively close to home. And a few of those are actually in the region that's poorly explored by the other surveys. So it kind of fills in the gaps a little bit compared to this bow tie shaped collection of galaxies. We're continuing to make observations of the universe around us. And so we'll fill in the gaps of that data set. And eventually we'll have a fuller picture of the universe around us. But right now we're going to keep flying in through the relatively nearby points of light that represent galaxies in our local region of intergalactic space. One of those is yet kind of hard to pick out in the middle of our image is actually our own Milky Way galaxy. And as we get close to it, we'll go ahead and we'll fade out the little circles that represent other galaxies to be able to focus on our own Milky Way. Here we can really begin to see the spiral structure of our Milky Way with older stars in toward the center of the galaxy, younger stars in general out toward the edges. We're about 2/3 of the way out from the center of the galaxy. And now as we grow closer to our location in this data set, we're seeing the stars closest to home, about 100,000 stars, whose distances have been measured relative to our location here on Earth. We'll approach our own home star, the sun, in our solar system. It's showed at the same brightness as other stars, but we'll fade it down so that we can see the orbits of the planets in orbit around the sun. and we'll eventually make our way in toward the third rock from the sun, our own home planet, Earth. I want to thank you all for tuning in to our tour of the universe here, and to take a look at where we are in the universe, how far things are in the universe, and also to get a little bit of background on a recent discovery about our amazing moon Titan of the planet Saturn. We appreciate you checking us out here on Facebook and on YouTube. Thank you again for tuning in. This is using OpenSpace software, which is free open source software supported by NASA. We'll be putting a survey in the comments if you have a chance to respond to it. And we appreciate your time. Thanks for joining us, and please have a great day.